We present SoundCam, a dataset for tasks in tracking, identifying, and detecting humans using room acoustics. The dataset contains 5,000 measurements of real room impulse responses and 2,000 recordings of music in 3 rooms: a controlled acoustically treated room, a real living room, and a real conference room. Across the data points in each of the datasets, we vary the presence of humans, their identities, and their locations. Every room has distinct acoustic properties. These acoustic properties don't just depend on the size and shape of the room, but are also a function of what objects are inside it, the shapes of these objects, and their materials and locations. SoundCam focuses specifically on the human as the object of interest. A room's acoustics will change if there is a person standing inside of it, and will also change depending on who that human is and where that human is located. We would like to know if we can observe these changes in the room's acoustics and use them to determine if someone is standing inside the room, where someone is standing in the room, and who they are. How do we measure a room's acoustics in a way that allows us to observe human-dependent changes? First, a room's acoustics can be observed directly by measuring the room's acoustic impulse response. Second, acoustics can be observed indirectly if there is sound being generated somewhere inside the room. For instance, the sound of a speaker playing music in the room will give you some rough information about the room's acoustics. This information can be recorded by setting up a microphone in the room. As a demonstration, this is what the room impulse response sounds like if the human is standing at the location shown in the video. If the person moves to another location, the room impulse response sounds nearly identical, but in fact has minor changes that may not be detected by a human. Next, this is what the room impulse response sounds like if a different human is standing at the same location. We show that our best baseline can correctly identify a human from a group of 5 distinct humans 64% of the time, using a single room impulse response. Finally, this is what the room impulse response sounds like if nobody is there at all. One of the tasks that we also show using our dataset is detecting if someone is in a room when there is music playing in it. This is what a clip of music sounds like in the empty room. And this is what the music sounds like if the human is standing at the location in the video. If the source music signal is given to the model, we show that our best baseline can use a single microphone to predict the presence of a human in a room with 98% accuracy. However, if the source music signal is unknown to the model, none of our baselines performs significantly better than chance. The SoundCam dataset consists of 5,000 room impulse responses and 2,000 recordings of music in 3 different rooms. Each recording or room impulse response is measured from 10 microphones placed along the room's periphery. For each recording or room impulse response measurement, the human's location and identity is recorded. In addition to the data points just mentioned, 100 measurements of the empty room's impulse response are also taken, as well as 1,000 recordings of music playing in the empty treated room. Here we show some example results from our best performing baseline for localization using room impulse response in our controlled acoustically treated room. This baseline model is a neural network trained on 800 room impulse responses from the same room in the exact same configuration and trained and tested on the same human. The average error is 46 centimeters across the test set. In addition to the 1,800 room impulse responses collected in the controlled acoustically treated room in its default configuration, we also collect another 1,000 room impulse responses in this treated room, but we place 4 thin fabric panels in different locations throughout the room. Thus, this dataset can be used to validate if methods to locate the human in the room are robust to changes in the room's layout, which could be an important subtask for real-world applications. In this experiment, we trained our model on recordings from the treated room without the fabric panels and tested it on recordings from the treated room with the panels. The baseline model shown previously performs significantly worse on the modified room. The average error jumps to 1.6 meters, which is worse than a hypothetical baseline that always predicts the average location from the training set. we discovered that none of our baseline models were particularly robust to changes in room layout. In addition to the previously shown tasks, we also provide baselines and results for several other tasks in our paper, including localization using music and generalizing localization methods to other individuals. In conclusion, we present SoundCam, a dataset of 5,000 real room impulse responses and 2,000 recordings of music in 3 real rooms. We showed that our dataset can be used for several tasks in localizing, identifying, and detecting humans using both room impulse responses and natural music, with varying degrees of success. We showed that our baselines fall short in the robustness to changes in room layout, so we hope to use our dataset to develop models that can generalize well to new room layouts and perhaps to unseen rooms. In addition, we show that some of our baselines can perform well when the source signal of the sound being played is known, but all fall short when the source signal of the sound is unknown to the model. We also hope to use our dataset to develop methods in our tasks of sound-based human localization, identification, and detection when the source signal of the sound is unknown. Thank you for listening, and we look forward to your valuable feedback.